In this video, we'll be looking at some problems from MyHrw 13.1. This section is dealing with using graphs and properties to solve equations with exponents. We're going to be seeing some equations with exponents in. I'm going to look at the problem that you're going to see the most of in this section. Here we have an exponential equation. We call it an exponential equation because our variable is in our exponent. 8 times 2 to the x power equals 128. We'll look at how to solve this equation. All right, the first thing we're going to do is isolate the exponential. What I mean by that is you're going to treat, let's rewrite this statement. We have our equation 8, and it has a parentheses, but I could put a little times operator there. We know connect means multiplied. 8 times 2 to the x power equals 128. You're going to isolate this whole exponential. So I'm just going to place a green circle around this and think about what will it take to get this green circle by itself. Well, here we have 8 times green circle is 128. We would divide by 8 on both sides. So dividing by 8 on the left and the right. 8 divides by 8 to leave green circle, but instead of green circle, we're going to write 2 to the x power, or exponential. And 128 divided by 8 is 16. So we have 2 to some power is 16. Well, how can we solve this? Well, we could imagine simply what 2 to what power would be 16. Hopefully you know that's 4. But the method we're going to see throughout this section is to get an equal base. That is, we're going to write 16 as 2 to some power. Well, it's 2 to the 4th. And when we arrive at this situation where we have the bases the same, 2 to some power is equal to 2 to the 4th, it must be true that these two bases are equal to each other, because our exponential is what's called a one-to-one function. For every x, there's exactly one y, and for every y, there's exactly one x. So in order for this equation to be satisfied, if the bases are equal, then the exponents must be equal. Generally speaking, it's going to look like this. If we have some number a to some power m, and that's equal to some same number a to some power n, then it must be the case that m and n are equal to each other. And I think that makes perfect sense. For a to the something to be equal to a to the something, those two somethings must be equal. If this statement is true, then it follows that m is equal to n. So what we're going to attempt to do is get the bases equal to each other, and then we can simply set the exponents equal to solve. All right. Also, we can, in the case of any function, we can simply take and graph both the left side and the right side. In this particular equation, we know that x is going to be equal to 4. That's our solution. So let's see how we can use our graphing calculator or Desmos to solve this same thing. I'm going to graph the left side. I'm going to call this one f of x. I'm going to graph the right side. I'm going to call this one g of x. And I'm going to see what value of x will make f of x equal to g of x. Let's take a look. To graph 2 to the x power, we simply hit Shift 6 to get the caret, puts the cursor in the exponent, x power. Here we see our exponential function, exponentially increasing. To the left, it gets closer and closer to the x-axis. That's our asymptote. And secondly, we'll graph g of x to be the constant 16. So this is the function y equals 16. We can't see it. It's a horizontal line at 16. We just need to scroll out a little bit, and here we see it. A horizontal line right through 16. Well, the solution is the x value at the point of intersection, 4. At an x value of 4, f of x and g of x is equal. G of x is always going to be 16. F of x will vary as x increases, y increases, but the specific value of 4 is the same for both of these. We can solve any equation with real solutions exactly like that. Graph one side, graph the other side, and find the x value where the two functions are equal. Let's look at a couple more problems from this assignment. Let's begin with problem number 2. The equation 2 equals 1.01 to the x power models a population that has doubled. What is the rate of increase? What does x represent? Well, if our base is greater than 1, we're going to see some increase. If it's between 0 and 1, we're going to see some decrease. Well, this, since it's 1.01, the increase is this 0.01 portion, or 1%. 0.01 represents 1%. X is the number of units of time. Frequently, with regards to our input variable and an exponential, we're going to be dealing with time. Number 3, can you solve exponential equations using both algebraic and graphical methods? Complete the explanation. Yes, you can. Yes, you can solve algebraically if you can rewrite the equation to have the same base on both sides, and that's what we showed just a little while ago, and then equate the exponents. That was the main point of the first problem. If not, you can always solve graphically by treating each side of the equation as a function and graphing the two functions to see where they intersect, and specifically to look for the x value of the point of intersection. So problem number 3 here, the main idea of 13.1. We can solve algebraically or graphically. This is the most important statement from this video, and in fact I want you to add this to your notes. Just add a single page to your notes, title it 13.1, using graphs and properties to solve equations with exponents, and copy down this statement. Can you solve exponential equations using both algebraic and graphical methods? That would be your essential question. Yes, you can solve algebraically if you can rewrite the equation to have the same base on both sides and then equate the exponents. If not, then you can always solve graphically by treating each side of the equation as a function and graphing the two functions to see where they intersect. Specifically, the x values of the point of intersection. Add that here, the x values of the point of intersection. Add this to your notes, take a picture of your notes, and then send that picture to me. In your notes, include the 2 example problems that I actually work out to show the algebraic method. I say again, you're adding this screen to your notes and those 2 problems. Take a picture and email it to me so I know you viewed this video. All right, we'll look at one more problem, and then I think you'll be in good footing to finish this on your own. Okay, so this will be problem number 5. Yours may be slightly different, but it'll be very similar. 7 times 2 to the x power equals 56. So we have the equation 7 times 2 to the x power is equal to 56. The first thing we're going to do each time is isolate the variable and the base. We call this an exponential equation because the input variable is in the exponent, or the variable in this case is in the exponent. So first thing I'm going to do is isolate that. So in this problem, I will divide by 7 on both sides. Dividing with 7, dividing with 7. 7 divides 7 to leave 2x. 56 divided by 7, that's 8. Now we want to write these bases the same. Here is a base 2, here is 8. Well, 2 to what power gives 8? 3. So I can write 8 as 2 to the 3rd. On this side, I have 2 to the x. I have written my bases as the same. Since my bases are the same, I know that those exponents must be the same. It must be true that x equals 3. Occasionally, we're going to have a more complex expression in the exponent than just x, but if it's just x, we're done at that point. Here, after that, we might need to go a little bit further. So we see x equals 3. That's our algebraic method. isolate the exponential, then get the bases equal to each other. Thus, the exponents must be equal to each other. Let's see that same thing graphically using Desmos. So on the left side, we'll have 7 times 2 to the x power. And on the right side, we'll have 56. Well, we can't see our horizontal line because we're only going up to 30. This is y equals 56. We need to zoom out a little further. And here we see our horizontal line. What we're interested in is where the two curves intersect. And more specifically, we're interested in the x value. We know the y value is going to be 56, but it's the x value we're interested in, 3. As we saw previously, 3 is the solution to this equation. That concludes this video. Remember to take the small amount of notes that I asked for. It's in the middle of this video. There were 2 problems I worked out. Add those to the notes as well. Take a picture of that and email the picture to me. Thank you, and y'all have a good day.